So welcome, my name is Thomas Hillen, and it's a great pleasure to have my Italian friend Davide Ambrosi here today for an interview. Please introduce yourself, Davide.
Yes, my name is Davide Ambrosi. I'm coming from Italy. Actually, I'm professor of mathematical physics at the Politecnico di Torino. My background is in physics, and then I moved to mathematics, to applied mathematics, and in particular, I'm very interested in the mathematics applied to biology and medicine.
Yeah. So you were somebody, at least in my view, who brought mechanics into math biology. So I think many math biologists did like this reaction diffusion equation modeling, like I do myself, and we ignore the mechanics for the moment. It's not so important. But you were the exact opposite, right? So did you have a background in mechanics?
Yes, actually, my background was in fluid dynamics, and later also in solid mechanics. And I was fascinated by this field. My mentor in this field was Luigi Preziosi in Torino. And he was working on the subject, and we discussed it. We wondered, but do you think that there is a role for mechanics in biology? And that was quite an unexpected question at that time, because most of the people were doing ODEs, ordinary differential equation,
Right, yeah.
Or the reaction diffusion equation at the time. But actually, the answer is yes. Mechanics, physics plays a role. There is there's a great interplay between physics and biology that is being revealed in the last years.
I mean, this is in the aftermath. It's a very natural question to ask, right? I mean, we are all mechanical individuals, right? There are pressures and deformations.
So migration of cells is a movement. There is displacement. There are forces that produce it.
Yes, right.
There is an energy that is spent to provide it. So energy is conserved. Where does it come from? How is it spent, and where does it go? So these are questions basically in physics. And of course, when you formalize these ideas into equations, mathematics show up.
Yeah, these are usually very complicated, aren't they?
I don't think so.
You don't think so? Okay.
I don't think so. Of course, you need some training. You need some training, maybe in fluid dynamics or in solid mechanics. But I like, actually, to rewrite the basic ideas can be written in very simple form.
Oh, I see.
Yeah. And basically, so I like when I do some seminars to go back a little bit to the elementary ideas, and that of course are translated into 3D, into large systems with some more formalism. But the basic ideas can be understood easily. So I would say there is a mathematics which is somehow devoted, specific of solid mechanics, tensor, for instance, or fluid mechanics. And but it has been developed for centuries therein. But at the end of the day, the real interest is in understanding what is crucial into this phenomena for biology.
Yeah, this is very good. Now I want to ask you about data, in particular data in the medical environment. So I think when you started looking at, let's say, cell movement, people would measure like the forces a cell generates on a surface somehow. But I think the measurements have changed, have they?
There is a book in Italian which is called, which takes his name from a famous work by an Italian writer.
Yeah.
And the name is basically the servant becomes the master. So the servant master is actually the name.
All right.
La serva padrona. So what happens that up to now there is a kind of mismatch between data and theory, which is in the past we did the theory, we had the very few data, and we compare the theory with the few data there were. Now the amount of data that comes from imaging is huge.
Right, it is.
So the question is, it's a mathematical one, it's also a philosophical one. Can you do a lot just using imaging with the mathematics, which is investigation in the data? Just using the data, you can avoid to use prediction. When I say prediction, I use a typical ordinary equation or differential equation that predict the evolution of the system. So at the beginning it was clear. The master were the equation and the data were something to be included. Now it may be that the data are the real master, and there is a role for models. There is a role for differential models, which is to keep the data informed of the physics and the biology. So it's fascinating. It's a challenging, but things are changing a lot.
I think so as well. It's a paradigm change a little bit, right?
It is.
Now, Davide, you have worked a lot with students, and you have
I did,
very good students coming from your group. Now, this paradigm change, would this influence the way you teach now, the next generation?
Well, this generation of students I deal with have a strong background in numerics. That was not the case for me and probably for you 30 years ago. And so they can deal with big three-dimensional problems with much more confidence. And this is a little bit one of the direction in our field. That is, look at the real three-dimensional development of, for instance, of tumors and try to track using imaging and try to give a clinical support in clinics for the possible evolution of the illness. And this is something that can be done by young people. Actually, they're always they often have a good background in this aspect.
Oh, that's really nice to hear. So, in general, what would you recommend young people to focus on if they want to enter the area?
Well, my recommendation is the following: don't be anxious. I'm trying to explain what I mean. I have many students. They are 34, 25 sometimes. And they want to start to enter the world of research, get in contact and produce papers and so on. But I would recommend that if you want to face mathematical biology and you really want to do something new, it's important that you have a strong background. So don't neglect your background in classical theory of PDEs. Possible, if you are interested in, for instance, my field, study classical method of applied mathematics to fluid mechanics, solid mechanics, differential equations, ordinary differential equations. And only when you are, I usually say, when you can stand on the shoulder of giants, you can face the new problem that are typically posed by experiments in biology, and you can deal with them. Something really new, which is not a poor translation of knowledge, which is not enough, in my opinion. You have a good background, you have a good basis, and now you understand that you can say something new in the application and in the math too.
Oh, very nice, yeah.
That's my opinion.
Yeah, well, that's a very good opinion.
Well, I was expecting a question from you, and I didn't know what to say. So maybe you will ask me, what will be the future? And I was wondering.
So what is the future?
I don't know what will be the future of this field. It seems natural to think, to be optimistic, and to think that all our work is not useful, not only from a point of view, of theoretical point of view, that's definitely true, this is already known, but also from the point of view of the applications. In some cases it's true. In some cases, there is an open question. So can we really support clinics with mathematics? Because sometimes people say, but you are just reproducing something that we already know. What is the new information that you can provide us with your mathematical models? Well, I don't know a definite answer. I can tell you, in some cases, mathematics has been also very helpful in applications. But in general, I don't know.
In particular in the cancer environment, right? It's sometimes difficult to pinpoint where actually did mathematically significantly improve the treatments and so on.
Because cancer is elusive. So every time you develop a strategy, there is something that medical doctors know that very well. That is, they develop a strategy to attack the tumor, and then there is something that we can avoid the medical solutions. And also mathematics is difficult to take into account the subtleties, so many subtleties from the point of view of self-organization of the tumor cells, differentiation, and so on and so on. And it's a very subtle matter.
Mm-hmm. It sounds like there's still lots of work for us to do.
That's positive information.
Yeah, then thank you very much for your time and for this wonderful interview.
It was my pleasure.
Yeah, I'm sure people will love what you said.
I hope so.